This video will cover a solution guide to problem 50 from chapter 15. A 1,750 Newton irregular beam is hanging horizontally by its ends from the ceiling by two vertical wires A and B, each 1.25 meters long and weighing 0.290 newtons. The center of gravity of this beam is 1/3 of the way along the beam from where wire A is attached. If you pluck both strings at the same time at the beam, what is the time delay between the arrival of the two pulses at the ceiling? Which pulse arrives first? Ignore the effect of the weight of the wires on the tension in the wires. First, let's start with a list of things we know. We're given the weights of the beam and the wires, and the length of the wires. In order to figure out the time it's going to take for each wave to reach the ceiling, we're going to have to know how fast they are traveling along their wires. The equation for the speed of a wave on a string is the square root of the tension in the string divided by the mass density of the string, where the mass density is simply the mass per unit length of our wires. So the easiest way to go about this is to just split the problem into 3 steps. First, we need to find the tension in each wire. Second, we'll find the velocity of the wave of each wire, and then we'll use that velocity to calculate the time it will take each wave to reach the ceiling. So let's get the tensions. The beam is in equilibrium, which means the summation of forces and the summation of torques will both be equal to 0. All forces are acting in the positive or negative y directions, so we can set all the upward acting forces equal to the downward acting forces. The same idea will apply to the torques. We will set the pivot point to be at the location of wire A. Doing so tells us that the force from the tension in B, which is acting at the full length of the beam away from the pivot point, is equal to the weight of the beam, which is acting 1/3 of the length of the beam away from the pivot. Simplifying, we find that the force from wire B is equal to 1/3 of the beam's weight. If we sub this back into the summation of forces equation, we find that the force from wire A is equal to 2/3 the weight of the beam. Now that we have the tensions, we can move on to finding the wave velocities. The mass density of the wires are the same, so let's quickly find the value of this. The problem gives us the weight of each wire, not the mass, so instead of the mass over the length, we will use the weight of the wire divided by the length times the acceleration due to gravity. This gives the mass density to be 0.0236 kilograms per meter. Now we can simply plug our values into our equations for the wave velocities in wire A and B. Before even plugging in the numbers, we can see that because the tension in A is bigger than the tension in B, the wave in wire A will be faster and will therefore arrive at the ceiling first. Subbing in the values we have calculated, we find that the speed of the wave in wire A is 222.34 meters per second, while the speed of the wave in wire B is 157.22 meters per second. Now let's figure out the time difference between the two reaching the ceiling. One of the first equations learned in this class was how distance related to velocity and time. Recalling this equation, we have that the time it will take the waves to reach the ceiling is equal to the length of the wire divided by the speed of the wave. Because we know that the time it will take for wave A to reach the ceiling is less than the time it will take for wave B, and the fact that we want a positive time difference, we will define the time difference as time B minus time A. Plugging in the expressions we have for time A and time B into this definition, and subbing in the length of the wires and the calculated velocities of each wave, we find that wave A makes it to the ceiling 2.33 milliseconds before wave B.